test 1 2 3 test 1 2 3ครับ test 1 2 3โอเคครับเสียงใช้ได้นะครับ test 1 2 3โอเคSo good afternoon, everyone. Welcome you to SCI33205. The same. There are 4 live channel in YouTube. It's up to you. There are 4 channels as usual. Okay, this one, which is broadcasted from Zoom. This is the live, which is taken by the mobile phone. And there are many channels. Okay, up to you if you want to see it in YouTube. And another channel is right here. This one. Okay, you can also watch it from this one. Okay. Okay. มาเรื่อยๆนะครับห้อง4จะนำห้อง5เยอะนะครับไม่รู้เพราะอะไรนะทั้งที่ผมเสียเวลาเซตเครื่องอะไรที่ห้อง4นะครับโอเคห้อง5ไม่ค่อยได้ใช้เวลาเซตเท่าไหร่นะครับคุณจะดูที่ YouTube ก็ได้นะครับแล้วพิมพ์ชื่อที่นั่นก็ได้ไม่ซีเรียสเลยผมไม่รู้ว่าเขาจะต่อซูมให้หรือไม่นะครับถ้าเกิดมีปัญหาซูมก็ดูที่ YouTube ได้ครับคือช่วงนี้มันเป็นช่วงที่เขาเรียกว่าอะไรที่มันหมดช่วงระยะอายุของซูมนะครับถ้ามีปัญหาก็ที่ YouTube นะครับOkay, we will talk about our story. We have finished. I would like to mention that next week you're gonna have the midterm exam, right? And if we cannot meet the final topic, which is the Faraday's induction law, I would ask you to watch the previous lecture in the last year until until the topic of Faraday's induction law. That's SCI 33205. Okay, you just no this one. You just go to the lecture last year, okay, because we don't have any more time, and that lecture will be given. I will make it available later. The last year, okay, in June or July or something like that. นะครับก็ถ้าเกิดไม่ทันนะครับเดี๋ยวผมไปปลดล็อกวิดีโอผมอัดเป็น private ไว้นะครับเดี๋ยวปลดเป็นฟรีนะครับเพื่อว่าให้คุณสามารถตามเนื้อหาจนถึงเนื้อหาที่สอบที่ในโรงเรียนต้องสอบครับถึง Faraday's induction law ครับเดี๋ยวคลิปเก่านะครับให้คุณไปดูแทนนะครับถ้าเกิดว่าไม่ทันในจะดูเรื่องนะครับสิทธากับรัชนนท์นะครับก็ถ้าเกิดใครเพิ่งเข้ามานะครับถ้าเราไม่ทันเรื่องเนื้อหา Faraday's induction law ใน2 ครั้งนี้นะครับก็ผมจะส่งลิงก์ให้คุณนะครับทางอีเมลนะครับหรือว่าคุณจะเปิดเป็นไลน์กรุ๊ปห้องก็ได้นะครับผมจะได้ส่งให้เป็นไลน์กรุ๊ปห้องนะครับเพื่อว่าจะได้สะดวกรวดเร็วนะครับในการติดต่อโอเค If there is no anyone who want to join Zoom anymore, I'm gonna go ahead with the story. here magnetic flux for M604 we arrive at this example, right? The example that we need to stop because the time was over last week. 64. We need to go to 64. Oh, I have to close this one because it's gonna consume the bandwidth. Okay, 64. 64, 66 something like that นะครับสำหรับคนที่ถามเรื่องเข็มทิศนะครับผมไปตามหาเรื่องราวแล้วนะครับเข็มทิศก็คือสร้างจากI need to mention it to you at the beginning of this chapter actually. Okay, the compass is made of actually the magnetic pole. Okay, where's that? Okay, here. ดังที่คุณบอกนะครับว่า compass หรือว่าเข็มทิศนั้นนะครับสามารถสร้างจากแม่เหล็กก็ได้นะครับสามารถสร้างจากแม่เหล็กก็ได้นะครับใครเพิ่งเข้ามาพิมพ์ชื่อนะครับOkay, the compass can be made of any kind of magnetized material. A simple compass consists of small lightweight magnets, okay, usually made by a magnetized metal needle or a nearly frictionless pivot point. One end of the needle is often marked with the N for the north, since the end of the needle always point toward the north. So it means I think I should bring you to the website. Okay. นะครับสำหรับคนที่ถามนะครับเรื่องว่าแม่เหล็กสร้างยังไงนะครับแม่เหล็กมันจริงๆมันทำแบบซับซ้อนก็ได้นะครับคือใช้ไฟฟ้าใส่ขดลวดก็ได้นะครับอย่างพวกเครื่องบินอย่างเงี้ยครับเขาต้องการทิศทางที่แม่นยำจริงๆเขาก็จะทำแบบนั้นนะครับwhere is that นะครับก็ถ้าอย่างเราใกล้สุดก็คือเขาบอกว่าให้เอาเหล็กเข็มก็ได้นะครับเข็มได้นะครับเข็มที่เย็บผ้าเล็กๆชุนมืออะไรอย่างเงี้ยนะครับก็เอาแม่เหล็กถาวรนะครับประจ่อหลายๆครั้ง20 ครั้งนะครับตัวโมเลกุลนะครับตัวโมเลกุลในเนื้อของเข็มนั้นนะครับก็จะจัดวางใหม่นะครับจัดวางพอเราเอาแม่เหล็กออกนะครับมันก็จะเปลี่ยนตัวเองนะครับกลายเป็นแม่เหล็กถาวรได้นะครับแล้วเราก็เอาเข็มนั้นนะครับไปวางบนเดี๋ยวผมหารูปให้นะครับ compass on waterเนี่ยครับวิธีทำง่ายๆเลยนะครับก็คือเนี่ยคุณเอาเข็มอย่างเงี้ยนะครับสำหรับเด็กคนโตก็ได้นะครับคือคุณเอาเข็มอย่างเงี้ยนะครับเอาไว้ข้างนอกก่อนนะแล้วคุณก็เอาแม่เหล็กถาวรจริงๆครับไปจ่อเข้าจ่อออกนะครับไปชิดๆใกล้ๆแล้วก็ดึงเข้าดึงออกครับชิดมันนะครับแล้วก็ดึงออกสัมผัสก็ได้ไม่สัมผัสก็ได้นะครับสัก20 ครั้งนะครับตัวเข็มนี้นะครับก็จะมีการจัดเรียงโมเลกุลเป็นแม่เหล็กนะครับมันจะมีขั้วเหนือนะครับขั้วใต้นะครับโอเคมาแล้วเราก็ไปเสียบกับอะไรก็ได้โฟมก็ได้นะที่เบาๆวางอยู่ในน้ำนะครับแล้วก็คุณก็จะเห็นเลยว่าพอโลกมันมีเส้นแรงแม่เหล็กมานะครับเส้นลูกศรวิ่งมาทางนี้นะครับมันจะพุ่งเข้าขั้วเซาท์นะครับขั้วใต้ตรงนี้นะครับแล้วก็จะออกขั้วเหนือนะครับมันก็จะบังคับให้เข็มเนี่ยจัดเรียงตามเส้นแรงแม่เหล็กของโลกครับนี่คือแบบง่ายที่สุดใช่ไหมครับส่วนแบบซื้อขายกันนั้นเขาก็คงทำดีกว่านี้แหละครับเขาคงไม่เอาเข็มง่ายๆอย่างนี้นะครับคงเป็นวัสดุแม่เหล็กจริงๆแต่ว่า มีน้ำหนักเบาให้น้อยที่สุดครับเพื่อว่ามันจะได้ไม่เกิดแรงเสียดทานครับอันนี้มันก็มีแรงเสียดทานนะระหว่างตัวโฟมกับน้ำครับแต่ว่าแรงเสียดทานนั้นน้อยนะครับแต่คุณไปเรียนเรื่อง liquid ก็จะมี viscosity ครับเรื่องความหนืดของเหลวนะครับโอเคพอจะตอบคำถามให้คนที่เป็นเจ้าของคำถามนี้ได้ไหมครับผมก็พยายามไปหามาแล้วส่วนที่จะเอาซับซ้อนมากกว่านี้พวกเครื่องบินนั้นจะเป็นไกโรสโคปคอมพาสนะครับไม่ใช่magnetized compass แบบนี้นะครับโอเคไหมนั่นก็จะอีกเรื่องหนึ่งไปเลยนั่นคือซับซ้อนเพราะว่าเขาต้องเครื่องบินมันผิดสัก1 องศาไม่ได้นะครับโอเคไหมไม่งั้นทิศทางก็จะพลาดครับโอเคthat's the additional question to what you have raised what you raised last time okay you asked me last time 66 64 something okay and this one okay has been changed flux okay change it to flux and this is Wilhelm Weber okay Wilhelm Weber worked closely together with Carl Friedrich Gauss. I think you would know Carl Friedrich Gauss. He was a German physicist. Okay, we're gonna use his surname quite often in the following examples. His name is Wilhelm Eduard Weber. He is German. He was German physicist. He investigated terrestrial magnetism and he invented electromagnetic telegraph. Okay, with Carl Friedrich Gauss. Okay, this person. If anyone wanna see him, okay, there were some statements about him where he was born, where he worked with university. The university that he worked is Georg August University in Göttingen. Okay, หรือว่าภาษาอังกฤษก็จะอ่านว่า George August นะครับ George August University of Göttingen ครับเมืองชื่อ Göttingen ครับก็เขาเป็น1 ใน 7 คนนะครับของเมือง Göttingen ครับที่ยกให้เป็นยอดครับ1 ในนั้นอีกคนหนึ่งก็คือ Carl Friedrich Gauss ครับที่เป็นยอดนักวิทยาศาสตร์ครับของเมือง Göttingen ครับใครอยากไปเรียนมหาลัยอันนี้นะครับก็สมัครไปนะครับเห็นไหมมีแต่คนเก่งๆนะครับเมืองผมอยู่ฮันโนฟาไม่ไกลจากเขานะครับแล้วก็ผมถามคนแถวนั้นนะครับเขาถามว่าสำเนียงภาษาเยอรมันอันไหนนะครับที่ชัดเจนที่สุดนะครับเขาบอกว่าสำเนียงของพวกคนเกิร์ทิงเกนนะครับก็คือเมืองนี้แหละเสียงชัดที่สุดนะครับเห็นไหมคือออกเสียงตรงที่สุดครับผมฮันโนฟาผมว่าผมก็ตรงแล้วนะแต่ว่าเขาบอกว่าเกิร์ทิงเกนนี่ออกเสียงตรงกว่าครับโอเคใครอยากไปอยู่ในโลกของนักวิทยาศาสตร์ชั้นนำนะครับในอดีตนะครับก็ไปที่เรียนที่เกิร์ทิงเกนนะครับทุกวันนี้เขาก็ไปอเมริกากันหมดแล้วนะครับโอเคyes Weber is his surname and we're going to use his surname in this example okay if there is no more student I'm going to close this one okay ตอบคำถามเรื่อง compass ให้คุณแล้วนะครับถ้าไม่พอใจคำถามอะไรพิมพ์มาครับหรือว่าเปิดไมค์ถามเขียนเมลได้ครับโอเค a plane surface with area 3.0 สำหรับคนที่เพิ่งมาทีหลังนะครับผมจะส่งลิงก์ที่หลังให้นะครับถ้าเกิดว่าเราเรียนไม่ทันถึงเรื่อง Faraday's induction law นะครับเพราะว่าสอบถึง Faraday's induction law ข้อเขียน2 ข้อสุดท้ายเป็นเรื่อง Faraday's induction law นะครับก็คือ generator นะครับหมุนขดลวดตัดสนามแม่เหล็กแล้วเกิดแรงดันไฟฟ้านะครับคุณต้องคำนวณแรงดันไฟฟ้านะครับโอเคa plane surface with area 3.0 cm square centimeter right this one but you know 1 centimeter is 10 to negative 2 right 10 with the power of -2 right but square means you have to multiply this one by 10 to 4 to negative 4 right it's 1 by 10,000 right is placed in a uniform magnetic field. Okay, for simplicity, we're gonna consider only the uniform distribution of magnetic field lines. That is oriented at angle of 30 degrees to the surface. Also, what does that mean? If you take a look at this one, okay, this is the plane. Okay, this rectangle here is the plane, and the area is 3.0 square centimeter. But in physics, okay, in our story โอเคครับมีพัทรชัยนะหมายเลข22นะครับพิมพ์ใน YouTube นะครับขออภัยที่เอ่ยนามครับเผื่อมันเน็ตมันล่มนะครับผมอัดไว้ในวิดีโอของ Zoom เลยนะครับ3.0 square centimeter but for us in physics we need to convert everything into the typical or standard unit in physics, right, which is square meter. So 3.0 square centimeter will be 310 to -4, as I told you. It means 10 to -2 square, so that's why we get 10 to -4. So that's really for us A, right? And the angle that the magnetic flux is directed will be 30 degrees with respect to the plane. Okay, but this angle is not usable for us in order to compute, right? Because we're gonna have phi BA cosine phi, right? Capital phi is BA cosine small phi, but small phi is the angle between the normal vector of that plane to the direction of the magnetic flux or the magnetic field line. Okay, this one. So once you have 30 degrees here, you need to find another angle, which is the actual angle that we can use in BA cosine phi. Okay, here from the last. Oh, why we have such a big. ทำไมมันใหญ่จังอ๋อเนี่ย okay. Because last time we have phi, right? B A cosine small phi, right? เสียงชัดเจนนะครับโอเคมาถ้าเสียงไม่ชัดเจนแจ้งครับ Yeah, phi is the angle between this is the angle between vector B, right? Vector B and sorry, it's the angle between B and A, right? So the angle between B and A, vector B is this one, right? This is the vector B, and vector A is the normal vector. So the normal vector is this one. So the angle between this vector and this one will be the angle here, which is 60 degrees. Okay. So in this case, phi is 60 degrees, or it's pi by 3, right? Okay. We arrive at this. Okay, at angle of 30 degrees to the surface. When they say 30 degrees to the surface, it means we need to find another one. Okay. Please don't substitute 30 degrees directly to the angle phi. Okay, you are gonna get the wrong answer. What is the angle phi? So we could find right here, right? Because from the typical geometry, if you have something like this is the plane, and you have the normal line, right? And yes, the normal vector will be right angle or 90 degrees with respect to the normal, right? Normal vector. and here is the plane, right? Here will be 90 degrees. Okay, but what they say is the plane is the direction of the vector B is made 30 degrees, right? So the phi angle is right here, right? So phi will be, what is that? It's okay. The combination of this one will be 90 degrees plus 30 degrees, right? So this one will be 980, right? 980 degrees minus 30 degrees plus 90 degrees, right? So it's going to be 180 minus 120 degrees, and that's 6 degrees. That's why the solution here has drawn 60 degrees. Okay, phi is 60 degrees to this question. The magnetic flux through this area is 0.9 milliweber. Okay, this is milliweber. Weber. Okay, you know that milli is 10 to negative 3, right? So it's 0.9 times 10 to negative 3 Weber, right? We cannot use milliweber because it's not standard international system of unit. I forget to mention. Okay, I will talk about it. Okay, B is 0.9 milliweber, right? And we can express it in the standard form times 10 to negative minus 3. Oh no, not milli anymore. It's going to be Weber. Okay, let's go to YouTube because I have prepared. Where is that? For those who want to know the actual no. Let me copy this ผมเตรียมให้คุณอยู่นะครับแต่ว่าลืมคำภาษาฝรั่งเศสโอเคthis one okay this one maybe.
Système international d'unité.
This is the actual pronunciation, okay, as I told you, SI unit.
Système international d'unité. Système international d'unité.
Okay, this is the actual pronunciation in French.
Système international d'unité.
Okay, they have meet
Système international d'unité.
each other and to form up the SI unit in
Système
France.
international d'unité. Système international d'unité.
Okay, I don't know. I know nothing about French, so
Système international d'unité.
this is the actual way to pronounce
Système international d'unité.
what she said here. Okay, what is it?
Système international d'unité.
Okay, you can practice yourself in YouTube.
Système international d'unité.
Okay, let's get back to us. In the actual unit for physics, we're going to use the SI unit. Okay, 0.9 times 10 to negative 3 Weber. Okay, you cannot use milliweber. Okay, you're going to get the wrong answer. Okay, they asked what is the magnitude of the magnetic field, right? So we start from phi, right, which is the BA cosine and small phi, right? What they want to know is this one, right? What is the magnitude of magnetic field? So they ask us this one, okay? What is that? Okay, in order to find B, we would transform this expression, right, to the expression for the B, right? Because you know that B is the magnitude, okay, the absolute value of the vector. So B here will be phi, right, divided by A and cosine angle phi. Okay, and yes, you can substitute it. Phi is 0.9, okay, times 10 to negative 3 milliweber, and you divide it by the area, which is what they say there, 3 times 10 to negative 4, okay, and cosine phi. Phi is angle 60 degree, right? So yeah, that's it. If you go ahead by hand, you're gonna get this is 1/2, right? 1/2. So you would have number 2 here, and you have 0.3 and times 10, right? 10 to power of 1, and of course you're gonna get 6. Okay, and the unit for B is Tesla, right? So we would write down here Tesla. I hope it's correct. 6 Tesla. Yeah, that's it. Okay, without any calculator, actually you can use only hand. Okay, is there any question to this problem? I substitute also the unit, okay, so that you can clearly understand. Okay, let's move to the next one. Okay, the best way to practice is to do several problems. Is to solve several problems. Okay, conducting circular loop. Okay, circular means you have something like this. Okay, round shape of the conductor of radius 0.25. Okay, we have here the radius. R is 0.25 meter. All right, is placed in the XY plane. Okay, we have here Z axis, we have here Y axis, we have here X axis. So the XY plane will be this one. Okay, this plane, that's known as XY plane, right? And that is a uniform magnetic field of 0.36 Tesla. So this is the value, the magnitude of the variable B, right? That points in the positive, the Z direction. So I think they would mean the magnetic field is directed upward like this. Okay, this is magnetic field line. Here this. Here would be magnetic field B direction. Because this is the positive set point. Calculate the magnetic flux through the loop. Okay, this conductor is lying on the XY plane. Okay, and magnetic flux, magnetic field line is directed or pointing upward like this, and calculate the magnetic flux through the loop. Okay, so they asked us about the phi. Okay, what is capital phi to this scenario? And suppose the loop is rotated clockwise around the x-axis. Is there any figure to that? No, there is no figure. Okay, no problem. Suppose the loop is rotated clockwise. Oh, clockwise around the x-axis. So if you have, if you draw the circular loop on the xy plane like this, it's gonna rotate clockwise. Okay, in the clockwise direction. So the normal direction now points at 45 degrees angle with respect to the z-axis. Okay, in the first scenario, this is the conductor loop, right? This is the conductor loop, and magnetic field is pointing in this way, right? In this way, that's magnetic field B. In the second scenario, the magnetic field clockwise is rotated. Okay, and now it becomes like this. Okay, it's oriented like this. This is the conductor loop, and magnetic field direction. Magnetic field direction remains the same. All right, remains the same. And the normal of this one is directed like this. Okay, and they say the angle here is 45 degrees. Okay, and recalculate the magnetic flux. Okay, what is the flux in the first scenario, and what is the flux in the second scenario? And they ask us also, what is the change in fact due to the rotation of the loop? So in physics, when they say something about a change, okay, the change, we would refer to scenario number 2 minus scenario number 1. Okay, in this case, they want us to find delta phi. Okay, delta phi is phi 2 minus phi 1. Okay, and what is that? All right. So let's open another page. Okay. In the first scenario, you can see that the plane, the circular loop is somehow this, right? Somehow this, and B is pointing upward like this. So what is the angle? What is the angle? What do you think? Phi is, what is that? This is the normal, right, to upward to the z-axis. So phi will be, of course, 90 degrees, right? So we will now compute phi at the first scenario, right? This is the first scenario. Phi 1 will be BA, A cosine phi, right? But in this scenario, A1 will be the same, right? B is 0.36 Tesla. A is the area, which is pi r square, right? And what they say is r is 0.25 meter. So we are gonna have here pi times 0.25 square, right? Or simply speaking, it's 0.625, right? So the unit here is square meter, right? Okay, what is the angle phi at this scenario? As they say here, phi is 90 degrees. So let's substitute it into the original expression. So B is 0.36 and A is pi and 0.25 square and cosine of 90 degree or pi by 2. ผิดตรงไหนบอกครับถ้าผิดตรงไหนบอกครับ that's equal to 1, right? And as you know, 0 point it's 0.09, right, times 4, right? And what else can we do? My, there's nothing, right? We need to use the calculator. Oh no, it's 1 by 4, right? This is 1 by 4 square, right? This one.
อาจารย์ครับ
ครับ
ตรงนั้นมันต้องเป็นสายไม่ใช่เหรอครับ
BA โคไซน์หรือไซน์ครับ
อาจารย์เลื่อนลงครับทำไมคอร์ด90มันเท่ากับ1นะครับ
Oh, sorry. Yes. No. Then what is the actual expression to this one? BA cosine, right? BA cosine, right? The formula is correct, but I don't understand why we get something like this. Sorry for that. I'm stupid. Thank you very much. ขอบคุณที่แย้งครับ This is B, okay, but the normal vector is also pointing in this way, okay. That's the normal vector of the area or the vector A, okay, and the angle here is not 90 degree. Thank you very much. It's 0 degree, okay. It's not 90 degree, it's 0 degree, so we have only 0 degree here. ขอบคุณที่ชี้แจงนะครับโอเคอันนี้เคลียร์แล้วโอเคso it's 1 by 4 square, right? 1 by 4 square, so you cancel it and you have only 0.09 by 4, right? You have 0.09 by 4 times pi, right? And what is that? Then it's, I don't know, 225, right? It's 0.0225, okay, pi, okay, and you leave it into the calculator, you're gonna get the result 0.225 pi.
normal line
เชิญครับ normal line ก็คือ vector normal ครับผมอธิบายที่ห้องชัดเจนเลยครับI will bring you to Google. They would have some photo.
อาจารย์ครับ
ครับ
มีเพื่อนจะเข้าซูมครับ
โอ้ขออภัยด้วยครับไม่ได้ดูเลยครับนึกว่าเข้ากันมาหมดแล้วมีนะครับเชิญครับขอบคุณครับขออภัยด้วยครับ Okay, the normal vector is the vector like this. Normal vector is somehow like this. Okay, if you have the plane, yeah, นี่เป็นระนาบนะครับแล้วก็เวกเตอร์ที่ตั้งฉากก็คือเวกเตอร์ที่มันพุ่งออกจากระนาบยกตัวอย่างเช่นเซกเตอร์นี้บริเวณพื้นที่นี้นะครับเราตัดทรงกลมโลกออกเป็นสี่เหลี่ยมเล็กๆสมมุติเป็นระนาบแล้วเวกเตอร์ที่พุ่งออกจากระนาบเนี่ยแล้วมันตั้งฉากเรียกว่าเวกเตอร์ normal นะครับโอเคไหม
โอเคครับ
พอเข้าใจนะครับโอเคเนาะไม่งั้นก็มีรูปอื่นเนี่ยครับมีเยอะแยะครับโอเค อันนี้เป็น side view นะครับเป็นด้านข้างนะครับผมลืมบอกไปว่า this is the side view โอ้ก็ลืมบอกไป this is the side view ก็คือมองด้านข้างนะเห็นไหมถ้ามองลงมามันก็จะเห็นเป็นวงกลมนะครับโอเค this is the side view and the normal vector is the vector that is that's directed upward okay from the circular loop นะครับขดลวดอยู่ตรงนี้ก็พื้นที่มันก็ต้องเป็นรูปวงกลมใช่ไหมเวกเตอร์ที่ตั้งฉากกับพื้นที่วงกลมข้างในขดลวดก็จะชี้ขึ้นมันชี้ทิศเดียวกับ b มุมมันก็เลยเป็นศูนย์นะไม่ใช่90 degree it's not 90 degree like this I'm stupid blur โอเคป่ะ90 0 degree okay we're gonna compute this one right 0.0225 pi ถ้าใครคณิตศาสตร์โอลิมปิกก็อย่าเพิ่งโกรธผมนะครับผมไม่ใช่ครับผมคิดเลขไม่เหลือ 0.0225 times pi it's 0.007 0.0707 okay approximately 0.707 and the unit is WB right Weber okay let's see whether it's yeah somehow it is okay 0.0707 okay and the next one is the second scenario right okay now the circular loop is rotated and it's aligned in this way okay and its normal vector will be like this or you can say it's vector A okay but the magnetic field will be still in the same way like this and what they say is the angle here is 45 degrees this is 45 degree right normal direction 45 degrees so that's correct okay now we get back to the same formula phi number 2 it's B and A cosine phi again okay but now our phi is 45 degrees so in the second scenario so B will be what is that then 0.36 0.36 right and A will be the same okay the area of the circular loop will remain the same the radius doesn't reduce so it's still 0.25 square but here we would have a new factor which is 45 degrees okay and 45 degrees mean 1 by square root 2 okay what we have calculated before is this one right what we have calculated in the previous scenario is 0.0707 right this one and this term is 1 by square root 2 okay and this is only the approximation not the actual value right yeah we will divide that one by square root 2 where is that okay by square root 2 oh no my so 0.599 okay approximately 0.05 unit is still the same approximate also here unit will be the same, which is the Weber. Okay, and what they want to know in the next question is delta phi, right? Which is the phi at the final one, say 2 minus phi at the initial, right? In the first stage. So it's going to be 0.0707 minus 0.05. Oh, I'm stupid. No. Final will be 0.05. 0.05 minus 0.0707. Okay, you're gonna get something that is not usual, and this is negative, right? So it's gonna be 207. Okay, and the unit will be again the same Weber. Okay, I'm not sure whether it's correct or not. Yeah, you would get somehow it's 0.05, okay, approximately, and this one is also approximate, only negative 0.0207. Okay, all right, that's the those are two examples about the computation of the magnetic flux. Let's go ahead with our story. Now we move from magnetic flux to the next topic, which is magnetic field from the current carrying conductor. Again, once we have the current that flows inside this conductor long straight copper wire, we can use the right-hand rule, right? The right-hand rules. Just curl or rotate your finger. Okay, 4 fingers. Use the right hand. Okay. As I mentioned, the positive charge doesn't move at all. Okay, the nucleus of any atom cannot move. Okay, this is only the artificial perception, okay, by human, because the actual particle that moves is electron. Okay, electron moves in this way. But anyway, use the conventional pseudo idea, okay, artificial idea. The current or the positive charge moved in this way, and we laid out our time direction in the same way as the current movement, and our remaining 4 fingers will give us the direction of the induced magnetic field. Okay, so if you have the cubic inside this long straight copper wire, if you cut this section, this plane, okay, what you will see will be only the dot. That's the head, okay, or the front line of the arrow. And what you will see here in this plane, on this plane, will be the tail or the rear part of the arrow. That's why you can see the X sign here. ก็คือเขาลองนะครับมาปล่อยให้กระแสไหลนะครับไปผ่านขดลวดตรงๆอย่างนี้นะครับ แล้วก็สมมุติเรามีกล่องโฟมแล้วกันกล่องโฟมเอาเส้นลวดเสียบเข้าไปนะครับแล้วตัดกล่องโฟมนะครับช่วงบริเวณนี้นะครับตัดแหว่งออกไปนะครับช่วงระนาบตรงนี้นะครับคุณจะเห็นแค่หัวลูกศรนะครับหัวลูกศรเขาจะใช้สัญลักษณ์คือจุดเห็นไหมครับจุดนะครับจุดคือลูกศรของสนามแม่เหล็ก B วิ่งพุ่งออกมาจากระนาบนี้นะครับโอเคไหมตามกฎมือขวาส่วนระนาบข้างล่างนะครับที่เราตัดข้างล่างนี้ก็จะเป็นเห็นแต่สนามแม่เหล็กมันปักลงไปใช่ไหมหมุนลงไปก็จะเห็นแค่ท้ายมันท้ายเขาใช้สัญลักษณ์ตัวขนไก่ใช่ไหมลูกธนูก็จะมีขนไก่ก็เหมือนเป็นตัว X ไปนะครับใช่ไหมกากบาทตัว X ไปโอเค that's the right hand rule we could find or determine the direction of the magnetic field induced around the long straight copper wire. And let's talk about this. Once you don't put any current into this long straight copper wire, and if you have 6 compasses like this. Okay, all the compasses will direct their needles to the Earth's magnetic field. Okay, for example, the magnetic, our North Pole, our geography North Pole is like right here. The magnetic field line will bring all the compass to this one. Okay, but once you let the current flows upward, okay, from the bottom to the top like this, and you use your right hand, okay, your curve or you rotate 4 fingers, you're gonna get the magnetic field like this. Okay, but usually when the magnetic field here would be stronger than the Earth magnetic field. Okay, when this magnetic field is stronger than the Earth magnetic field, this will have more potential, okay, to keep the needles or the areas of all those compasses, all 6 compasses, to be around here according to the right hand rule. Okay, นะครับมันไม่ได้อยู่ห้องจริงมันก็ทำมือให้ดูไม่ได้นะครับ Okay, the induced magnetic field will go around the long straight copper wire in the green circle here. All right, and let's talk about Biot-Savart law. Biot-Savart law. Who is Biot? Who is Savart? มันลืมทำรูปมาให้ดูนะเป็นฝรั่งเศสนะถ้าผมจำไม่ผิดนะ Okay, Biot-Savart. Here. Jean-Baptiste Biot. Okay, this person, Jean-Baptiste Biot. And another person who also invented, it's known as Felix Sabat. Not Felix Sabat. Felix Sabat is the trainer of the football team. Okay, football squad. Jean-Baptiste Biot was a French physicist. Okay, also astronomer, mathematician. I don't know why most physicists work also in mathematician. Okay, Felix Sabat, quite old. We don't have even his photo because in that generation there is no mobile phone, there is no camera, there is no digital camera, there is no film camera at all. Felix Sabat was a French also physicist and mathematician. Okay, he is known for Biot-Savart. Okay, for us here. So you get to know Biot and Sabat. Let's talk about his discovery, the law. The magnitude of magnetic field B could be computed from any distance. Okay, if you stay here, you can observe the magnetic field. If you far away from the magnetic field, from the long straight copper wire, you can still get the magnetic field, but the magnetic field will be weaker. And it's given by this one. Okay, mu0 I. Okay, I is the amount that you put into the long straight copper wire, the current. Okay, the amount of the current you let it flow in the long straight copper wire. Okay, what is mu0? Mu0 is the standard constant. It's permeability of free space in that matter. For example, if we talk about vacuum, we will get mu0. Okay, it's the permeability to let the magnetic field form up in that area. Okay, in free space or the vacuum, we're gonna have mu0. Okay, if you use metal or something like that, this will be less. Okay, the metal will let you have magnetic field more difficultly. Okay, more difficult than typical free space. 4 pi times 10 to -7 is the standard value in Tesla meter and by ampere. Okay, and that's the numerator. Okay, what about the denominator? Denominator will be only the the distance, okay, along the circle path, okay, or we can say it's circumference. All right, it's the circumference. 2 pi r. R is the radius that you stay far away from the center of that long straight copper wire. Okay, if you more far and far, right, you will get weaker magnetic field or magnetic flux density. Okay, according to the Biot and Sabat law. Okay, it's not difficult, right? Pi is pi, right? And do we cancel pi here? Okay. Yeah. From the Biot Sabat law, you stay at the radius r from the center of this conductor, and if the current flows in this way, okay, upward like this, you can use your right hand, and your 4 fingers will represent the magnetic field B. Okay, magnetic field B right here. All right. Let's talk about the first example related to the Biot-Sabat law. A long straight direct current. Okay, we will say direct current. Do you know direct current? Right. The direct current means the current that flows in only a single direction. Okay, but on the other hand, the alternating current, okay, which is used at our home, okay, at our house, we're gonna have the alternating current, and the direction of the alternating current is alternate. Okay, they change, go and back, go and back. I'm not sure whether we would have any video simulation or something. Okay.
What is the difference between AC and DC currents? E and point P. That
Hi, this is English with an hour, and you should come with me to
advertisement.
italki. Ta-da! italki.
proper direction. It doesn't change its proper direction. Useful work due to its need, and then a current moves in both direction.
Okay. AC means the current goes and goes back. Okay, return to the same place. Go and go back. Okay. This is AC. But the direct currents mean the current flows only in a single direction.
Back from point Q to point P. So we say that this wheel moves in one direction. Secondly,
direction, like
this wheel is moving, so it can also do some sort of useful work due to its kinetic energy. Now consider here. So the motion of this wheel has no direction because polarity remains constant.
Okay, there would be a better figure to represent AC and DC. If not, then okay. Another way is to
Now, before we
look
go
at
over this problem,
the
let's talk about the divided by the square root of 2
okay. The AC will be in
So
the
it's 10
sinusoidal
amps
form like this.
over the square root of 2.
You will see it later.
60
This is
hertz.
DC. Okay.
It
DC
constantly reverse 60 times in times per second. Graph and make it look like this.
DC will give you the
So you have
curve like this.
sinusoidal function.
Okay, this is DC. Okay, the voltage is constant. The AC will have some fluctuation like this. Okay, go and back, go and back. Okay, positive is going. Okay, or forward direction. Negative means the returning direction. Okay, okay, you know something about DC and AC. Long straight direct current power line carries the current of 100 ampere. Oh, it's very large, 100 ampere. A swarm of bees builds a hive next to it. Okay, ก็เป็นฝูงผึ้งมาสร้างรังครับ and oh, they are clever. Okay, The bees are clever. They use the Earth magnetic field as the reference direction when they want to orient their honeycombs รังผึ้งที่อยู่บ้านเขานะครับ at what distance from the power line is the magnitude of the magnetic field from the current equal to the magnitude of Earth's magnetic field, which is about 5 or 50 micro Tesla, or 5 times 10 to the -5 Tesla. Okay. Okay, don't worry about the orientation of the honeycombs by the bee, but what they want to know here is bee on Earth will be equal to bee caused by the long stretch power line. Okay, so bee Earth will be equal to B, which is caused by power line. Okay, and B on Earth is this value, what they have provided here. All right, so we need to find B power line, right? B power line could be calculated from ในกี่โมงผมต้องปล่อยคุณ14 ป่ะ 14:00 เนาะเพราะว่าออนไลน์เขาให้เลิกก่อนถูกไหมครับเดี๋ยวผมขออนุญาตเช็คเวลาแบบนี้เดี๋ยวปล่อยคุณแล้วคุณไม่มีเวลาเบรกไปเรียนวิชาอื่นครับจำไม่ได้สักทีนะครับOkay. 12:40. Okay, 14:20. But I have to let you have the break, right? For 20 minutes. So 14, we're gonna leave our lecture. Okay, the amount of the magnetic field caused by the power line could be borrowed from this expression, BO Sabat or mu0I divided by 2 pi r, right? So B power line at what distance, right? They want us to find distance. So this is the cable line, the power line. And if we stay here, distance R or something like that. And at this point, the magnetic field caused by let's say the current is in this direction. This is the B. Okay, B power line. We will have its magnitude equal to the magnetic field caused by the Earth. Okay, the Earth's magnetic field. So B power line will be mu0I divided by 2 pi r, right? But they want to know r, right? What is r? So let's open the next page. We solve this equation for r, right? So r, the radius, will be mu0I divided by 2 pi b power line, but B power line is exactly the same as B Earth, right? So we can have mu0I divided by 2 pi and B Earth. Okay, that's the same value. Okay, and mu0 is 4 pi times 10 to -7, and I is the current. They say 100 ampere. Oh, and I would say in French they don't pronounce ampere. Okay, let's hear what they pronounce นะครับถ้าไปแล้วก็ไปให้สุดนะว่าเจ้าของภาษาเขาออกเสียงไงนะครับ Ampere is the English pronunciation. This one.
We are looking at how to pronounce this word as well as how to say more interesting and often confusing words, including from science, so make sure to stay tuned for those. So how do you say it? Well, he was a French mathematician and physicist, and this base unit of electric current that we know today was named after him. So how do you say it? Well, in French, his name is said as Ampere, Ampere. In English, this is generally said one of two different ways. Either in British English, Ampere, Ampere, or in American English, Ampere, Ampere. Which one is the closest to the French? Certainly the British English pronunciation. Ampere is way closer to the French Ampere, or the original name. And now you know. More videos here on how to...
Okay. Ampere, Ampere in French, okay, or in British English, Ampere, okay, and in US, United States English, they say Ampere, okay. Doesn't matter, okay. Yeah, 4 pi times 10 to 7, and the unit of the current is ampere, okay, and yeah, here is 100 ampere, okay, 10 to 2, right, and 2 pi at the denominator, and we have here the earth, which is 5 times 10 to negative 5 Tesla, right? Let's compute this by hand. We can cancel, that's number 2, right? And you have 2 by 5 times 10 to 5, right? 5, 7, so negative 0. So it's equal to 0.4 meter, right? If I am correct. Okay, let's talk about distance R. 0.4 meter exactly. Okay, now we go to the next example. Find the current in the long straight wire that would produce a magnetic field twice the strength of the earth at a distance 5 centimeter from the wire. Okay, and now in this example, they ask us to find this amount, okay, which is I. Huh? What happened? เดี๋ยวนี้ชอบมี error ครับไม่รู้เป็นที่เครื่องผมไม่ได้ restart หรือเป็นอัปเดต iOS หรือยังไงไม่ทราบเริ่มมีปัญหาอย่างนี้ครับโอเคokay, they want to ask us to produce magnetic field twice the strength of the earth. Okay, it means we start from B. Okay, magnetic field should be twice, mean double the value of magnetic field on Earth, right? Caused by the and they want to find I, right? We start from the Biot Sabat B mu 0 I and 4 pi R, right? And in order to find I, we move everything to the left hand side. Okay, I will be 4 pi times R and B and divided by mu 0. But R will be is twice, okay, 4 pi and 2 B earth, okay, divided by mu 0, okay. So no, not 4 pi, it's 2 pi m stupid. 2 pi, okay. You can see that this is actually like that ครับชอบเกิดปัญหาอย่างนี้ครับ4 pi times b earth ถ้าไม่ไหวผมจะขอรีสตาร์ทเครื่องครับเคยเกิดปัญหากับปริญญาตรีครับตอนสอนครับอย่างนี้เหมือนกันรีสตาร์ทแล้วหายโอเค4 pi is 4 pi นะครับมาอีกแล้วครับเส้นที่แบบไม่ได้อยากให้มีนะครับเกิดขึ้นเองครับ4 pi and b earth is 5 times 10 to มาอีกแล้วครับ 10 to negative 5 divided by mu 0 which is 4 pi มาอีกแล้วครับมาก่อน4 pi มาแล้วครับมาก่อนจะทำได้ไหมอย่างนี้นะครับ times นะครับเส้นตกเดี๋ยวขอรีสตาร์ทเครื่องแล้วครับนะครับกลายเป็นวาดรูปเลยครับเดี๋ยวสักแป๊บเดียวผมขอออกจากซูมนิดนึงครับเพราะว่าเขียนปากกาต่อไปแล้วหรือไม่ผมก็ปิดบลูทูธแป๊บนึงครับของ่ายๆก่อนครับปิดบลูทูธแป๊บนึงโอเคยังไม่ต้องรีสตาร์ทก็ได้นะครับโอเคhere is 4 pi ยังเกิดอยู่ครับtimes 10 to negative 7 right so you can cancel this right and it's gonna be 5 times 10 to 2 โอ้นะครับเกิดเส้นมาผมไม่ได้อยากให้มีครับ it's equal to 500 ampere โอเคจบข้อนี้เดี๋ยวขอรีสตาร์ทครับโอเค500 ampere is there is y25 ผมย้ายผิดto b mu 0 I and if you quantify I 2 pi r b is mu 0 I by 2 pi r right 2 pi r b by mu 0 b is mu 0 I is 2 pi rb by mu 0 2 pi rb by mu 0 yes that's correct it's 4 right 4 pi
มันเป็นนี่อะไรอย่าง
the radius right distance of 5 cent ผมลืม r ครับตรงนี้ครับ my god r and there should be also r here r is my god missing 5 times 10 to negative 2 right and what you have there is yes you have to multiply here 5 times 10 to negative 2 okay and 25 ampere only I think yeah 25 ampere โอเคขออภัยด้วยครับลืม r นะครับเขียนเป็นสีแดงไม่ใช่ครับ r is radius which is only 5 centimeter 5 centimeter means 5 times 10 to negative 2 so that's why 25 ampere let's move to the next part which is the magnetic force on current carrying conductor. But before that, it's not convenient for me to write down something. Let me restart the iPad. Okay, but first of all, I would need, oh my God. I would need to get out of the Zoom for a while. Okay, เดี๋ยวผมขออนุญาต restart เครื่องแป๊บหนึ่งนะครับ Felix display. Okay, and again, share the screen. See that here. My God. Okay. Okay, we arrive at this page, right? The story, the topic about magnetic force on a current carrying conductor. Well, once you have learned before, right? FQVB, right? Positive charge. Okay. Current is actually the flow rate of the positive charge per time, right? Here you have the charge moving in this direction with velocity here, drift velocity. Okay. Let's say the average velocity of all the particles, the positive charge here, is in this way. Okay, but this figure is not true. Okay, as I mentioned it quite often, the positive charge cannot move inside the conductor, only the electron, which is the negative charge, right? Okay, the negative charge move in the opposite way, those are electrons, but this is the artificial notation. The positive charge moves in this way, okay, upward. And according to the FQVB conventional direction prediction, the V is right here, right? B is pointing. What is the direction of the magnetic field? Once we see the X symbol here, what does that mean? It means the magnetic field is directed or pointing into the plane of this lecture note, okay, into this slide. Okay, เห็นสัญลักษณ์เครื่องหมายคูณอย่างนี้ครับก็หมายความว่าสนามแม่เหล็กนั้นชี้เข้าไปในแผ่นสไลด์อันนี้นะครับเอกสารประกอบการเรียนนี้นะครับก็คือเห็นท้ายมันครับคือสนามแม่เหล็กพุ่งเข้าไปในแผ่นกระดาษนะครับ so once you rotate your four fingers from the vector V to the vector B, which is pointing into this plane, this lecture notes, we're gonna get force direction like this, okay, from V to B, right? And yeah, once you have many charged particles, force will be in the same way, okay? And if you have the length, because the conductor or the copper wire would have as an amount of the length, right? Let L be the length for this long straight copper wire, and yeah, we have current here. It means the positive charge is moving in this way. Or in horizontal orientation, which is taken from another book, the positive charge is moving from left to right, and there is cross-sectional area. Okay, let's say the conductor is made of cylindrical shape. Okay, the cross-sectional area will be circle. All right, and if the magnetic field is directed into this plane หมดเวลาแล้วครับเดี๋ยวขออธิบายรูปนี้จบก็เลิกครับเดี๋ยวค่อยขึ้น29ทีหลังครับyes you can have FQB again, right? FQB, let me draw the expression. QV cross B. KR. พอรีสตาร์ทแล้วไม่มีปัญหาเลยครับ V to B, okay, V to B. You rotate your 4 fingers from the vector V to the second vector, which is vector B. Okay, from V by B, you get the force your thumb direction upward like this. Okay, and this is the length of interest for the conductor. Okay, we will see how we get transform FQB to FILB later. Okay, today we finished everything. See you on Friday morning, right? I would ask you to do the homework only once a week. Okay, today there will be no homework. We will talk about the homework later on Friday. Okay, see you on Friday. Bye bye. If you have any question, just let me know. Okay, I'm gonna try to deliver the answer to your question. If not, then bye bye ครับสวัสดีครับคนไหนไม่ได้พิมพ์ชื่ออย่าลืมนะครับอยู่ YouTube อยู่อะไรก็พิมพ์มาครับ Okay. I hope that no one want to join the Zoom meeting. Okay, still I see that.นี่นะครับถึงผมต้องหลอกไปเรื่อยๆก่อน Okay, we arrived at okay, we arrived at the topic of the magnetic field, right? Like this, right? And you have seen already that magnetic field line starts from the geometric south pole to the, and it reaches the geometric north pole. Okay, the geometric north pole is known as the south pole for us in magnetic field orientation, because the south pole means the area that receives the magnetic field line, and the north pole is the area where we create or start to send the magnetic field lines, right? And the reason why we have magnetic field is the following: the true source of the Earth magnetic field is electric current, because as you can see from volcano and so on, there is molten iron that moves out of those volcano, right? And yeah, actually inside the Earth we have hot iron that always move in the core, and magnetic poles, because the hot iron always move, the magnetic poles actually moves also every year around kilometers, okay, several kilometers. And interesting fact is that the physicists or the scientists believe that in few million years ago, actually the direction of the Earth magnetic field should reverse, okay, should have the opposite direction. And they say that few million years ago, the Earth magnetic field start from this one to this one, okay. And due to the chaotic movement of the core fluid, because they move easily or freely inside the core of the Earth, the Earth magnetic field changes a little bit over the years, okay. Now we move to the topic of magnetic flux, which is the next thing. What is magnetic flux? Magnetic flux is the way we express how strong the magnetic field per area. Okay, flux is the number of field lines. Okay, let's simply speaking. For example, this is the curvature surface, and if you divide the whole surface into a tiny amount of area, for example, the square here, and we assume that the tiny amount of the area is planar, right? Planar is smooth planar like this, and assume that the magnetic field line is uniform. What does the uniform mean? The number of magnetic field lines per area are quite the same, okay, for all of this area, and that's uniform magnetic field. For example, for one piece of the square, we have only a single arrow of the magnetic field line, and that's a typical way to measure. Okay, all these lines will be 90 degrees to the plane that they emerge from. If the area is bent a little bit in this direction, the magnetic field line should shake a little bit too, okay, to this direction. The concept of flux is similar to the electric flux. In Gauss' law, magnetic flux is defined the same way as electric flux, and it's very close to, it has a close relation to the magnetic field lines. That's the behavior of magnetic flux. The magnetic flux is proportional to both the strength of the magnetic field passing through the plane and the associating area. The magnetic flux is denoted by phi b, okay, the capital phi, and assume that there is a magnetic field B as shown in figure 25, like this. Okay, this is the curvature surface. Okay, it's not the planar smooth area. Let's divide the curvature here to be a tiny piece of square, and if the magnetic flux density or the magnetic field line points in this way, is pointed or directed in this way, okay, is not the usual way we compute or observe the magnetic flux, right? We need to transform this component to this one. What is this one? This is the component that is perpendicular to this plane everywhere. Okay, in 360 degrees. Okay, you can measure this normal vector to the plane, and you will get all the time 90 degrees. Okay, that's the right angle, and of course you can also project this one to another component which is right angle from each other, but this one is not counted because its orientation is not perpendicular to the plane of observation. Okay, this is directed in the same way as the plane. Okay, we cannot count it. We would count only the strongest one, which is 90 degrees from the plane. This component is called B with subscript perpendicular. It's not transport levers, okay, in reverse direction. It's a perpendicular symbol, and here is the parallel symbol for the magnetic flux density. Okay, in this way. Okay, the component of magnetic field B is normal to the surface delta A. This is delta A, and this one is the component that is projected to be normal to the plane. Okay, that's important. B with perpendicular symbol means this component. Okay, and if we want to find the magnitude of this one, we could take the absolute value to that, and that's the absolute value of vector B projected onto cosine phi, and here is vector B, the absolute of vector B, and here is the magnitude of this one, okay, times cosine phi. It's typical projection onto two perpendicular components. Okay, and phi is the angle between the normal vector and the magnetic flux density vector or the magnetic field lines. Yeah. Okay. And the tiny amount of the magnetic flux could be found from this expression. If you have more area, you will get more flux. Okay, and the magnetic flux density will be uniform, will be the same for everywhere, right? This is the simple assumption. And the B perpendicular will be expressed as B cosine phi like this. Okay. Let's talk about the better view. Okay. BA cosine phi, BA delta cosine phi, B delta A cosine phi is computed from this dot product. You know dot product, right? Should I mention something about dot product to you? ผมต้องกล่าวเกี่ยวกับเรื่อง dot product ให้คุณไหมครับเช่นว่าอาจารย์ยกตัวอย่างให้ดูหน่อย dot product เป็นไงครับถ้าบางคนผ่านเคยเจอมาแล้วก็ไม่ต้องก็ได้นะครับแต่คุณครับอยากให้ผมยกตัวอย่างไหมอย่าง cross vector เนี้ยผมก็ยกตัวอย่าง cross vector ให้คุณดูนะครับผมไม่รู้ว่าคุณมีพื้นฐานเรื่อง dot product ไหมครับแต่ว่า 6.4 เขาไม่ต้องนะโอเค up to you if you want to see an example of dot product of two vectors just let me know. Dot here is the dot product operators of two vectors and in general this component is different for some points on the surface. Okay, we consider a tiny amount, that's why we say delta A, and we get a tiny amount of magnetic flux too. So B is magnetic flux per A, that's the density, right? But phi B is magnetic flux, so it should be the product of magnetic flux density and the observed area นะครับก็ถ้าใครอยากดูที่ YouTube นะครับก็เข้าไปดูที่ YouTube นะครับมีทั้งเวอร์ชั่นเห็นรูปผมและไม่เห็นรูปผมนะแต่ส่วนใหญ่จะถ้าเป็น YouTube ที่ไม่ใช่ซูมนะครับมันจะเป็น1080นะก็คือมันจะชัดมากครับแล้วก็เป็น60เฟรม per second ด้วยนะครับก็จะสมูทมากกว่านะครับของซูมมันได้แค่720นะครับคุณลองเปิดดูเองนะครับอยู่ที่ YouTube นะครับก็อย่างนี้ครับอันนี้จะเป็นของซูมนะครับ720อันนี้จะเป็นถ่ายจากมือถือไปนะครับมือถือเครื่องที่ผมไปตั้งถ่ายที่ห้องเรียนคุณครับแล้วก็อันนี้ถ่ายนะครับจะเป็น1080ครับจะละเอียดกว่าแล้วก็อันนี้จะเป็น1080อันนี้ก็กล้องอันนี้เป็น OBS เหมือนกันครับก็จะเป็น1080 60p ครับจะละเอียดกว่าอีกอันนึงก็เป็นที่ตรงนี้นะครับถ้าคุณอยากเห็นมุมมองนี้นะครับอยากเห็นมุมมองนี้ก็ให้มาดูช่องนี้นะครับ OBS number 2นะครับ to YouTube you get อันนี้ก็ชัดมาก1080 60p 60 frame per second okay let's get back to our story if the surface is planar is smooth okay and คือคุณจะไม่เข้าซูมก็ได้ครับแล้วคุณก็พิมพ์ชื่อไว้ที่นั่นครับผมเห็นหมดนะครับผมมอนิเตอร์อยู่ครับif the magnetic field B is uniform over the plane surface we don't have to do any calculus okay infinitesimal delta phi by delta A or integration phi is B integration B delta A no for us in the high school we're gonna see only the multiplication expression okay not integration or differentiation the perpendicular component B with this one okay and the angle phi are the same at all position okay on the surface so we would have phi B equal to B perpendicular times A but B perpendicular itself is equal to B at cosine phi right so that's why we have BA cosine phi now let's talk about the unit of system I don't know how to pronounce it appropriately or correctly the SI unit of phi B okay magnetic flux is known as 1 Tesla right B is Tesla A is square meter right so it's going to be Newton meter per ampere right but the person. Okay, let's talk about system international, how to pronounce. Okay, this is
Système international d'unité.
this is the actual way to pronounce
Système
what the so-called SI unit. Okay, because they made the first conference to form up the unit for everything in France. So they use the French language, the French to become the unit. Okay, the SI unit. But in English, we would say international system of units, right? But this one is French. Okay, they order the words quite similarly to Thai language. Okay, the noun and the adjective, right? Noun and adjective. It's like in Thai language, right? We have noun and the adjective. Okay, but the way to pronounce, unfortunately, I have never been in France, so you can listen to this.
international d'unité. Système international d'unité. Système international d'unité.
Okay, I may not try to pronounce it
Système
because it's quite
international
difficult.
d'unité. Système international d'unité. Système international d'unité.
Okay, this is the way to pronounce. You can practice yourself in YouTube. Okay, the person who observed this quantity, the magnetic flux, is Wilhelm Weber. And once he passes away, once he died, we will not call Newton meter per ampere anymore. It's going to be called 1 Weber. Okay, the last name from Wilhelm Weber, or his the family name Weber. So who is Weber? Oh, we have to move to this file, right? $60. $60. Okay. The unit, right? Okay, the unit is this person, Wilhelm Eduard Weber. Okay, he was a German physicist, and he investigated terrestrial magnetism, and he invented the electromagnetic telegraph with this person. Okay, Professor Gauss. Okay, they work at Göttingen, Georg August University at Göttingen. Okay, Göttingen is the name of a city in Germany. Okay, it's the city of education. Okay, apart from Bonn, or many cities would be full of great education system or area นะครับถ้าใครนะครับสนใจในวิทยาศาสตร์นะครับแน่นอนครับคุณโตขึ้นชั้นระดับปริญญาตรีนะครับคาร์ล เฟเดริก เกาส์นะครับก็คือ professor เกาส์เนี่ยคิดอะไรไว้เยอะแยะทิ้งไว้บนโลกนี้มากมายครับเขาเป็นคนที่สมองเขาปราดเปรื่องมากครับถ้าใครอยากไปเรียนนะครับก็ที่ professor เกาส์อยู่ที่ Georg August Universität Göttingen ก็คือGeorge August University of Göttingen นะครับก็คือเมือง Göttingen ชื่อมหาวิทยาลัยว่า George August นะครับก็เวเบอร์ก็เป็นคนที่อยู่ในยุคเดียวกับเกาส์นะครับก็ร่วมมือกันคิดอะไรหลายอย่างนะครับรวมทั้งสิ่งที่เรากำลังเรียนด้วยนะครับก็คือ Magic Flux นะครับเวเบอร์วิลแฮมเวเบอร์นี่ถือเป็น1 ใน 7 คนครับที่ถือว่าเป็นตัวหลักเขาเรียกว่าอะไรดีตำนานของ7 คนในเกิร์ทิงเกนครับมหาวิทยาลัยเกิร์ทิงเกนเพราะว่าสร้างสิ่งที่มีชื่อเสียงไว้กับจากมหาวิทยาลัยนี้เยอะนะครับเขียนมา7 คน2 คนที่ผมทราบตอนนี้ก็คือเวเบอร์กับคาร์ล เฟรดริก เกาส์ครับใครอยากรู้ว่า7 คนมีใครบ้างกดในอินเทอร์เน็ตนะครับถ้าใครอยากไปเรียนก็อยู่แถวๆเมืองที่ผมจบเอกมาครับผมอยู่ฮานโนฟาร์ก็เกิร์ทิงเกนไปก็ไม่ไกลมากครับแต่ผมไม่เคยไปครับเกิร์ทิงเกนเขาบอกว่าที่เกิร์ทิงเกนนี่ถามคนเยอรมันครับเขาบอกว่าพูดภาษาเยอรมันนี่ชัดเจนนะครับแล้วก็สะอาดที่สุดคำว่าสะอาดไม่ได้หมายความว่าพูดสกปรกละมกนะครับหมายความว่าพูดแล้วไม่มีสำเนียงท้องถิ่นมากที่สุดนะครับก็คือพูดชัดเจนมากที่สุดครับผมว่าตอนผมอยู่ฮานโนฟาก็ถือว่าชัดแล้วนะเขาบอกว่าฝรั่งบอกว่าที่ให้ไปเกิร์ทิงเกนนะครับจะพูดภาษาเยอรมันชัดกว่าที่เราอยู่กันนี้อีกนะครับก็ถ้าใครอยากไปศึกษาครับก็ไปที่เกิร์ทิงเกนนะครับเป็นมหาวิทยาลัยชั้นนำอันหนึ่งครับของประเทศเยอรมนีนะครับโอเคyeah once Weber passed away we used his surname instead of the Newton meter per ampere is quite long right just simply use take his surname Weber okay let's consider several situations or the orientation of the plane that we want to observe. For example, the magnetic flux density is directed in this way horizontally from left to right, and the normal vector of this plane. Okay, the plane, this plane is oriented like this. Okay, it's perpendicular to the direction of the magnetic flux density B. Yeah, but note that the normal vector is in the same way as the magnetic flux density. You may ask me what is the normal vector. Okay, คำว่า normal vector normal คืออะไรนะครับเดี๋ยวผมหาให้นะครับเพราะว่า604ก็ถามนะครับ Okay, let's talk about this. Normal vector is the vector that is perpendicular to the area you want to find. Okay, for example, on Earth, at this segment, at this small area, the normal vector should be pointed this way, not this way or not this way. Okay, exactly right angle from that plane. If you don't understand, take a look at this. The yellow area is the plane, and normal vector is N1, for example. If you measure the angle between this vector to the plane, you will get right angle like this. In any direction, you will get always 90 degrees. You move in 360 degrees, you will get only 90 degrees from the plane. Okay, or another opposite way is N2 like this. Okay. Anything else? Okay, if you have curvature, the normal vector will be different. Okay, if the area is bent somehow like this, is directed in this way, normal vector will be point all the time right angle or perpendicular to that cross section area. But if this one try to bend a little bit to the right, the arrow will also directed in this way. Okay. If you still don't understand, here is another example. Normal vector in this way, normal vector in this way. All right. พอได้นะครับเข้าใจนะว่า normal vector อะไรคือเวกเตอร์ที่มันออกมาจากระนาบนั้นแล้วมันตั้งฉากครับเข้าใจไหมถ้าระนาบมันโค้งมันก็ต้องออกคนละมุมครับถ้ามันเป็นเรียบมันก็เป็นธรรมดา ได้ครับเนี่ยครับอันนี้มันเป็นพื้นเรียบมันก็มี normal vector อันเดียวชี้ฟัดไปมุมใดก็90หมดเลยนะครับ alright พอเข้าใจนะครับin this figure ถ้าไม่มีใครแล้วขออนุญาตปิดอันนี้นะครับเพื่อว่าจะได้ใช้พื้นที่เต็มๆบนหน้าจอครับ Okay, the normal vector is directed in this way and the angle between normal vector and the magnetic flux density is 0 degree so that's why we have 50 here มีใครเปิดไมค์ไว้ไหมครับเดี๋ยวผมขออนุญาตปิดไมค์ไว้นิดนึงนะมีอาคิรานะเปิดไมค์ไว้นะครับปิดไมค์นะปิดไมค์ทำไงอาคิรานะครับช่วยปิดไมค์หน่อยครับผมกดปิดไม่เป็นครับในซูมครับthis one โอเคปิดทันแล้วครับโอเคthat's the magnetic field, right? The angle between magnetic flux density and the normal vector is 0 because they point in the same way. Okay, and we can derive once we get a smooth surface from this expression, right? Because magnetic flux density is magnetic flux per area. That's density. The unit for magnetic flux density is 1 Tesla is equal to 1 Weber per square meter, right? And once the plane is oriented in a different way like this, and here is the vertical line, and here is the horizontal. This is the normal vector of that plane, right? And the blue one is the magnetic field lines or magnetic flux density vector in the horizontal way like this. And if this area has the amount of A, okay, square meter, and normal vector will be like this, we can measure the angle between the magnetic flux density vector to the normal vector, and that's the angle phi. Okay. If the plane is rotated a little bit like this, you can see that the magnetic flux density vector is in the same way. A normal vector of this plane is upward like this, and you have 90 degrees like this. Of course, once you substitute phi into the original expression, cosine phi like this, right? Cosine phi, yeah. When phi is 90 degrees or pi by 2, cosine is 0, and 0 times anything will remain 0. So that's why at this orientation, this one here, we will not get magnetic flux at all because cosine phi is 0, cosine of 90 degrees is 0. Okay, let's consider the first example about the magnetic flux problem. We have a planar surface with area 3.0 is placed in a uniform magnetic field that is oriented at an angle of 30 degrees to the surface. So it means we have this figure. I don't have to draw at all. I need not to draw at all. We have the horizontal magnetic flux density vector like this, and the plane is oriented like this. Okay, let's say they say the plane is oriented at 30 degrees to the surface. Okay, this is magnetic flux, and the angle to the surface will be 30 degrees. But it's not the angle that we could substitute into cosine phi. Okay, please be careful. The first question is, what is the angle phi? So phi is not this one, okay? Phi is measured from the magnetic flux density to the normal vector of that plane. Okay, at the scenario, the normal vector is going to be in this way, right? The right angle from the plane. And if you measure with respect to the magnetic flux density vector, it's going to be something else. Okay, let's draw it. If this is the plane, right? And we have this is the side view. Okay, side view. This is vector B, right? And normal vector will be this way. This is normal vector or vector A. Okay, and here they have right angle to this one. So this one is 90 degree. What is about this? This is 30 degree as they claim here. Okay, the surface is oriented at 30 degree to the magnetic flux density vector, like that. And yes, you can see that the summation of these three angles, 1, 2, 3, will be 190 degrees, right? So the angle phi, which is the amount, which is this amount, okay, this is angle phi. Phi could be found from 180 minus, okay, deduced by these two angles, 180 degrees, because this is the long straight angle, right? The summation of the angle should be 180 degrees. So minus 30 degrees plus 90 degrees. So we're going to have 180 minus 120 degrees, and that's only 60 degrees. So it means the angle here between the normal vector and the plane, the normal vector and the magnetic flux density vector B is only 60 degrees. That's why they have here 60 degrees. So phi in this case is 60 degrees. All right, let's talk about the second question. If the magnetic flux through this area is 0.9 milliweber, you know the prefix unit, right? Milli is 10 to negative 3. And what else? Weber is Weber. And the question is, what is the magnitude of the magnetic field in this scenario? So they asked us about this quantity. What is that? Okay, or simply speaking, this is actually B. All right, the variable B, that's the magnitude of the magnetic field. Okay, so how could we find the variable B? We have to start from the typical expression, right, studied by Weber. Phi B is BA cosine angle phi, right? In this scenario, phi is 60 degrees, right? Phi is 60 degrees, so we know phi. B is the magnetic flux density, right? And they want to know B, right? In this scenario, B, we have to arrange this expression to be in the form for B, right? In the form of B. So we get B equal to phi by A cosine phi, small phi. All right. And the big capital phi is what they have provided here. Phi is 0.9. 0.9 times milli is 10 to negative 3 Weber, and divided by A. A is the area, and that's 3 times 10 to negative 4. And cosine phi, right? Cosine of what? Cosine of 60 degrees. So cosine of 60 degrees. Okay, and you get 0.9 times 10 to negative 3 divided by 3 times 10 to negative 4 and times 1 by 2. Okay, and you have here 0.3 times 2 and 10 times 10 to negative to 1, right? So it means that you get 6 Tesla only. Okay, I'm not sure whether it's correct or not. Yeah, 6 Tesla. Okay, all right. Let's move to the next one. A conducting circular loop. We don't have. Okay, conducting circular means you have a long circle and then you round it as a circle. Okay, I don't know how many loops they want. Okay, and here is the circular conductor loop. Okay, they say this circle has the radius of 0.25. Okay, they also provide the information here. It's 0.25 meter. Okay, it's fine because meter is already the standard distance unit in the SI system, right? And there is a uniform magnetic field 0.36 Tesla that points in the positive z direction. So they talk about a Cartesian coordinate that has 3 axes. Z, X, and Y, right? Let's say if the conductor is located around here, okay, and it points in the the magnetic flux density is in this way. Okay, that's the magnetic field B. Calculate the magnetic flux through the loop. Okay, so what is phi in this situation? And in the second situation, suppose the loop is rotated clockwise around the x-axis. It's rotated like this. Okay, or in the clockwise, right? It's rotated like this, and the normal direction now points at 45 degrees angle with respect to the z-axis. So if you take a look at the side view, this is B vector, and this is also the z-axis, right? But the conducting loop is now oriented like this, and the normal vector is directed like this, so that this is the right angle. This is normal vector of the area A, right? So what is the phi in this scenario? Phi will be the angle here, and they say 45 degree. Okay, 45 degrees here. Okay, and with respect to z-axis. Okay. Z-axis is this one. Recalculate the magnetic flux through the loop at this moment. Okay, so this is phi 1 in the first scenario, and here is phi number 2 in the second scenario. All right. Yes. And the third question is that they want to know the change in flux due to the rotation of the loop. So they want to find delta phi. Okay, in physics, we're gonna get phi 2, okay, the final state 2 minus the first state, okay, phi at the first state. Oh, now we will start to calculate it. Right. The first question is what is in the first scenario? What is phi in the first scenario? What is that, right? And if the loop is rotated quite a little bit. Oh no, in the first question. Phi in the first scenario will be BA, right? BA cosine phi, and phi in this scenario, okay, is on the XY plane. So in the side view, we're gonna have here. This is the circular conducting loop, and the normal of this plane of this loop is this one. This is normal vector of the area A, right? And the magnetic flux is directed to upward to Z axis, right? So we're gonna have flux like this, right? So the angle here, this is magnetic flux B. The angle will be phi is 0, right? Because they are directed in the same way. And let's talk about the area. The area of circle. You have a circle like this, and you have radius r. So area of circle will be pi r square, right? And r is what they have provided, which is 0.25 meter, right? So once we substitute everything, phi at the first state, B magnetic flux density 0.36, and A is the area, which is pi times r square, right? R is 0.25 pi, and r is 0.25 square cosine, right? Cosine of what? Cosine of 0, right? It's not cosine of 0 degree or 0 radian up to, it will be the same. Yes, of course, we have here 0.36 and 0.625 times pi, and here is number 1, right? Cosine 0 is number 1, and you put it into the calculator. Okay, 0.360625 pi, right? .36 times 0.625 times pi will be 0.707 approximately. 0.0707. A unit of the magnetic flux is, of course, Wilhelm Weber, right? It's WB. Okay. And in the second question, the argument to find the magnetic flux once the circular loop rotates a little bit at 45 degrees. So now in the second scenario, phi number 2 is 45 degrees. Okay, yeah, let's compute it. Okay, it's again the same B and A cosine phi at the second stage, which is only 45 degrees. Okay, we'll substitute everything, which is 0.36 Tesla, and A is the same 0.625 and pi, right? And the cosine now is cosine of 45 degrees. Okay, cosine 45 is 1/√2, right? 0.36 and 0.625 625 and pi, and here you have 1 by square root 2. Okay, just divide the former value by square root 2. We have the result here, and we have to divide by square root 2, right? It's approximately 0.5. Okay, and the unit for phi is Weber, right? This is the magnetic flux. It's approximately 0.5 Weber. And the last one, the last quantity they want to know is the delta phi, right? Delta phi. So in physics, phi, when we talk about a change of something, it's going to be phi at the final state minus phi at the initial state. Okay, final minus beginning, initial state. So it's phi at the first stage minus phi in the second stage. Oh, sorry, second minus 1. So phi 2 is 0.5 minus 0.0707, right? This one. Is that correct? 0.5. Okay. Yes. You will get. Oh, I'm stupid. 0.7 first. 0.07 minus 0.5. Oh, no. Is that correct? 0.36625. R squared. Oh, 0. R squared 62536 and pi. Right, and divided by. I don't understand why we divide by square root 2, but we get greater value. 366. Is that right? Times pi 2. Okay, 0.7, not 0.07, my God. Without 0. 707, okay, and here is 0.5 minus 0.707, and you're gonna get something about negative 0.207 Weber, right? Let's check the result. Yeah, 0.0207, 0.05. My God. Why? ครับ
มันน่าจะผิดที่ว่า 0.25 ยกกำลัง 2 มันต้องเป็น 0.0625
4 ตัวนะผมก็ลืมไปครับ yes is incorrect right there ขอบคุณมากครับ คิดเลขผิดครับ 0.0 okay 0.0 เพราะจำได้ว่าห้องก่อนหน้านี้ห้อง04มันต้อง0ก่อนนะครับ K and you get 0 in front of that 0.707 and yeah is 0.05, and that's why once we have the deduction or the subtraction here, 0.5, 0.07, and we have 0.0207. Okay, like this. Sorry for that. Yes, this is quite important. But ไอ้เครื่องคิดเลขนะครับก็มือตรงนี้ก็พลาดนะครับ Okay, 0.0207 Weber, which is exactly the same thing here. All right, we approximate this one, right? 0.05 and here 0.0707. All right, two computational examples about the magnetic flux. Now we move from the topic of magnetic flux to the next one, which is magnetic field caused by a current, okay, that moves in the conductor. Okay, let's consider the yellow pipe here is a solid conductors made of metal. It can be either copper, silver, gold, iron, or any kind of metal that can carry the electricity. Okay, let's say we have the current that flows from the left to the right here. But I have to mention that we cannot believe in this idea because the positive charge doesn't move at all, right? The particle that moves inside the conductor is electron. Electron moves from the right hand side to the left hand side. But he will use something that is easily understandable. They use the direction of the positive charge. Okay, so it seems somehow like we have positive charge moving from the left hand to the right hand, but actually the positive charge doesn't move at all. All right. Okay, let's say we have the current here. It seems like the positive charge moving like this. So we can use the right hand. Okay, we lay down our thumb direction along this way, and we have the 4 fingers, okay, that represent the induced magnetic field. Okay, if you have a box like this, okay, it can be styrofoam or something like that, and you put this conductor inside this cubic form, and you cut this vertical plane, and you cut at the horizontal plane here and here in the front plane. What you can see from this plane is that there will be dot symbol, right? What is that? The dot symbol means what we could observe from the magnetic at this area is only the front, okay, the face of the vector B, okay. It's like the arrow. Once you see only the front view of the arrow, it means it is a tiny amount. So that represent the front area of these magnetic field lines. And if this one is directed into this plane, we would see only the tail part or the rear part of that arrow, right? Which is the magnetic field. So that's why we see the X symbol or the cross symbol here. This is the rear part of the tail of the vector, okay, or the arrow. Yes. This plane will let you see only the rear part, and this plane will let you see only the front part, and this plane will let you see all the curve V direction of the circle magnetic field. Okay, let's move to the next one, next figure. If you have a conductor here and you have the plane like this, okay, and you have 6 compasses, and at the moment we didn't inject any current through this conductor at all, so all the compasses will direct their needles to the same way as the Earth's magnetic field. For example, this is the north geographic north pole. This is the south geographic south pole. The magnetic field starts from the geomagnetic south pole to this one, okay, which is actually the north magnetic pole, right? The magnetic field line will be in this way, this way, this way, and that's why we get the orientation of all needles in these 6 compasses in this way, okay. But once we inject or insert the current through this long straight copper wire, because this magnetic field will be stronger than the Earth magnetic field, okay, the compasses will lay down their needles or their arrows according to the right-hand rule. The circular magnetic field induces a circular magnetic field like this, okay, and that's why you see the compass that shows the orientation of all needles like this, okay, in the circular way, okay. This is from the right-hand rule, okay, and let's talk about the BO Sabat law. ผมต้องปล่อยคุณเท่าไหร่ครับ15เขาเลิกที่ 16.00 ใช่ไหมก็จะปล่อยคุณที่ 15.40 นะครับ 15.40 แล้วให้คุณเพราะมันคุณมีโควต้าเบรก20 นาทีนะครับในการเรียนออนไลน์เนาะเดี๋ยวครับระหว่างที่เรียนนะครับผมก็ขอแจ้งนิดนึงครับผมอาจจะสอนไม่ทันเนื้อหาที่สอบนะครับสอบจบที่เรื่อง Faraday's Induction Law นะครับเดี๋ยววันนี้นะครับจะไปปลดล็อกคลิป YouTube เก่านะครับของรุ่นพี่นะครับซึ่งผมล็อกไว้ให้คนอื่นดูเป็น private นะครับจะปรับเป็น public นะครับแล้วก็ส่งให้คุณดูนะครับคือเนื้อหาจนถึง Faraday's Induction Law นะครับคุณไปดูเตรียมไว้นะครับตัวผมนี่แหละครับเป็นคนสอนครับแต่ของปีที่แล้วครับสอนรุ่นพี่คุณครับก็ให้ไปดูครับดูก็คือศึกษาด้วยตัวเองครับก็เพราะว่าเวลามันไม่ทันครับก็ให้คุณไปนั่งดูแล้วก็ใช้ในการสอบครับเดี๋ยวผมส่งให้ครับเช่นเดียวกัน604ด้วยนะครับโอเคมาเดี๋ยวปลดล็อกจาก private เป็น public ให้นะครับเพื่อคุณไปดูนะโอเค we arrive at the BO Sabat law the magnitude of the magnetic field B, okay, caused by the current. Okay, you could find the orientation or the direction of the magnetic field already, right? From the right-hand rule, this is what we well known. But qualitatively, okay, what about the quantity? Two French physicists, Biot and Sabat, who is Biot? Okay, Biot is this person, Jean-Baptiste Biot. I'm not sure whether I pronounce it correctly or not. This person, okay, Jean-Baptiste Biot. And another person is Felix Sabat. Okay, Felix Sabat is a French physicist and mathematician. This is Felix Sabat. We don't have any further photo from him like a real person. Biot was the French physicist too. Okay, French physicist and astronomer. Okay, both discovered this relation B0I by 2R. N is the number of brow of the conductor that you have. Okay, we have only a single conductor, so this is only one, and capital N is 1. So B is mu0 I divided by 2 pi R. What is mu0? Mu0 is the constant, okay, permeability of free space or the vacuum. Let's say it's equal to 4 pi times 10 to -7. This is what you may have already seen in the light speed calculation, okay, at the beginning of this subject. B is the magnitude of the magnetic field B in Tesla, and I is the current. Okay, the current unit is this one. What is that? The unit of the current. Okay. Here is the actual pronunciation. Okay, this is the actual pronunciation of this word.
We are looking at how to pronounce famous scientists.
Oh, sorry.
Bonjour, this is...
ใหม่จากดาวนี้
Oh my god. Advertisement.
จอยแต่งงานกันนะ
12 ด้วย
We are looking at how to pronounce this. A French mathematician and physicist, and the space unit of electric current that we know today was named after him. So, how do you say it? Well, in French, his name is said as ampère, ampère. In English, this is generally said one of two different ways. Either in British English, ampère, ampère, or in American English, ampere, ampere. Which one is the closest to the French? Certainly the British English pronunciation. Ampere is way closer to the French ampère, or the original name. And now you know. More videos.
Okay. Okay, in French, it's gonna be called ampère. Okay, ampère. And in English, it's gonna be called ampere. Okay, in British English, ampere. In US, okay, United States, English, they're gonna call ampere. Okay, so whatever way you pronounce, okay, is understandable. Okay, so the unit of the current is ampere, and R is the shortest distance to the Y. Okay, is the shortest. Okay, if you draw the curve like this, it's not the shortest distance. Okay, the shortest distance is you have the long straight line like this. Okay, okay, you may say, this is also the distance, but it's not the shortest one. Okay, you just move in any direction. It's not the shortest one. The shortest one is the long straight line like this. Okay, yes, this is the way to get the direction, right? By using the right-hand rule, you have the induced current I, you have the current, okay, injecting current, and you get the induced magnetic field B at the distance R. Okay, let's talk about the first example for the BO-Sabat formula. We have a long straight direct current power line. So what is direct current? Direct currents mean you have only a single transmission direction of the current, but the alternating current is the system that has the current that move forward and the current move backward. I'm trying to find any video for you in YouTube. Okay, this one.
In this video, I am going to discuss electric conductor in 1 second,
Okay.
then the amount of current
Here.
passing through the...
Oh my God, what?
Hello, welcome to the interior today.
In this video, I am going... Electric current is represented by...
Okay, here. Okay, the electron moves from the left, from the negative side to the positive side, right? It means the current moved from the positive side. Okay, yeah, that's direct current. Okay, it all moves
and I is equal
in this
to
way.
Q by
Oh
T.
my God.
Q is amount of charge and T is time. If 1 coulomb of charge pass
Okay,
through a
and they don't have. Okay, here is the alternating current, the AC.
AC current, which we normally use at our homes. In
Okay,
case of
it's
AC
very
source,
fast.
both the
Okay,
magnitude
to understand. First, both polarities will change with time. Okay, it can be either negative or positive. Once this one is negative and this one is positive, the current, the electron will move from the negative side to the positive side. But once this one changes to negative side, the electron will move from this side to this side, and this one is positive. Okay, but it happens very
and
fast.
direction of current changes with time. By changing magnitude of the current, we mean that the amount of current passing through the conductor rise and fall. And by changing direction, we mean that charges oscillate back and forth. Current duality of these two terminals changes with time. The number of times polarities changes per second.
Another way, because they show the very fast frequency, right? We're going to see something. Oh, no. AC, DC current. Okay.
What is the difference from point P to other points X and Y? Let an electron is present.
The current moves only in this direction. That's the DC, direct current. Okay. And the alternating current, they move in this way, and also they move in this way too. Okay. After a certain time. And a better picture to differentiate them is to look at the current per time. I'm not sure whether they have the curve. They don't have that curve. Okay, it's this one.
Now, before we go over this
okay,
voltage and therefore
this is direct current. Okay, the voltage is
AC circuit,
a certain value at time at any time, but the AC
and make it look like this.
The AC will be like this. Okay.
So you have a sinusoidal
waveform like that. Okay. At this location, the voltage is positive. The current moves from the left to right. At this location, the voltage is negative. The current moves from the right to the left. Okay, and it changes again. At this area, it's positive. The voltage is positive. The current moves from this one to this location, and at this location, at this area, the current moves from the right to the left, like this all the time. Okay, that's the difference between DC and AC. All right. And here, what they talk about is only DC direct current, and the cable lines carry 100 ampere. Swarm of bees, okay, builds a hive next to it, and it is hypothesized that the bees use the Earth magnetic field to make the reference point, okay, in order to build up their hives. Okay, when orienting their honeycombs, okay. At what distance from the power line is the magnitude of the Earth, is the magnitude of the magnetic field from the current equal to the magnitude of the Earth's magnetic field, which is about 5 times 10 to 5 Tesla. So how far, right? This is the conductor, and they want to see how far the height of the honeycomb of the bees. Okay, so that they could receive the same magnetic field as the magnetic field on Earth. Okay, caused by the Earth. So they just want to know what is the distance here. Okay. Yes. Yes. We have B Earth, right? Equal to B from the power line. Oh my God, error, my God. Power line น่าจะเป็นเพราะผมทำปากกาตกบ่อยครับเจ๊งเลยครับ yes but B power line is computed by mu0I, right, divided by 2 pi r, right, and they want to find the distance d, which is actually r. Okay, r or r, right? So we solve this expression for r. We get r equal to mu0I divided by 2 pi b Earth, right? 2 pi b Earth. All right, and you leave everything. Mu0 is 4 pi times 10 to negative 7. I is the current, which is provided here. 100 ampere is 10 to 2, right? 10 to 2. And here is 2 pi times the Earth magnetic field, which is 5 times 10 to negative 5. All right. And you can cancel these, right? This is number 2 by 5, right? You get 2 by 5. And this is times 10 to 7. Oh no. Yeah, 10 to 0 actually, because it's gonna they're gonna cancel each other, right? So it's 0.4 meter, right? Yes, is that correct? Yes, 0.4 meter. So now we move to the next example, which is the long straight copper wire. Okay, I'll find the current in a long straight copper wire that would produce the magnetic field twice the strength of the Earth's magnetic field at a distance 5 centimeters from the wire. So how could we derive this? All right. We have here a long straight copper wire, and they want to know how much current you should insert onto this long straight copper wire. And the distance you want to observe, this is the person who want to observe. The distance is equal to 5. But in physics, we're going to express it in meter, right? M, right? Okay. So R is 5 times 10 to negative 2 meter. And the amount of the magnetic field you could observe is B Earth. Okay, what you can observe here. ทำไมเลอะเทอะอย่างนี้ไม่รู้นะครับผมยังไม่ได้เขียนอะไรเลยครับขึ้นเองครับโอ้ my god สงสัยไม่ iPad เสียก็ปากกาเสียครับ so this one is B Earth นั่นครับขึ้นนี่เพิ่งรีสตาร์ทมาจากห้อง605นะครับ B Earth โอ้ my god Okay, B earth, the amount you could receive is B earth, and just from the twice, right? Twice B earth, so this is 2 times B earth. Okay, so we will use the typical expression, right? 2B earth แต่สีน้ำเงินไม่เป็นครับงงมากครับ 2B earth ถ้าผมไม่รู้ว่าเป็นเพราะอัปเดต iOS หรือเปล่าครับ is mu0I divided by 2 pi r, right? But they want to get the value of I. We have to move everything to the left hand side for I, right? I will be 4 pi r b earth divided by mu0, right? So let's substitute it. I will be 4 piเป็นเหมือนกัน times r, right? R is 5 times 10 to negative 2, and b earth is 5 times 10 to negative 5, right? It's like that, right? And mu0 is 4 pi times 10 to negative 7, and you can cancel these pair, right? And you would have 25. My God, 25. Times the 0, 10 to 0, which is actually 25 ampere, right? Is that correct? Yes, 25 ampere. Okay, and that's it for this problem. Now we move to the next topic, which is Malik force on current carrying conductor. This is the conductor that carry the shard moving, right? And in conventional way, they call it the positive shard. Okay, but in fact, in nature, positive shard cannot move inside the current conductor. Okay, only the electrons, like the metal. Okay, the positive charge moves in this way upward like this, and we have the cross symbols in this area. It means this is the rear part or the tail part of the arrow of the magnetic field. Magnetic flux density, vector B, right? The magnetic flux is pointing into this plane, right? You can start to cross to get the direction by using the formula F equal to Q V cross B, right? Q V cross B, so you start from vector V to vector B, right? By using right hand, you're gonna get the F direction to the left hand like this, okay? And the current is flowing like this. That's why we get a positive charge moving in this way, okay? And a certain length of the conductor is L, okay? But the time is over right now. I'm gonna let you leave this classroom, okay? Anybody who didn't write down your name in the channel, in the text chat list, please write it in the Zoom, right? Yeah, or you are in YouTube, just write in YouTube. Okay, we would not have the homework for today. Okay, on Friday we will have the homework. Okay, only one homework per week. That seems to be sufficient for you. Okay, if it's too much, it's gonna be trouble to you. Okay, I'll see you on Friday. I'm gonna send the link for several contents until you reach the normal the midterm exam. Okay, if you have any question to this lecture, please let me know. Otherwise, we are gonna leave this lecture right now. ครับถ้ามีคำถามใดครับก็โปรดถามนะครับถ้าไม่มีแล้วก็จะปิดแล้วนะเพื่อว่าคุณต้องเบรก20 นาทีนะครับจากข้อตกลงของเขานะครับ EP โปรแกรมนะครับโอ เคครับ ก็บ๊ายบายครับ สวัสดีครับ605ครับ